Okay, so let me explain this concept. So last night I had an interesting experience. Woke up and had my meditation where I had an experience of sort of taking some concepts I was working on and seeing the big picture. So what this relates to is that reality has this nature that includes things that are just imagined, right? Things that are not real. Basically, all things that you can ever imagine are a part of reality somehow. And so the math, right, where some clues show up is throughout history, throughout mathematics, throughout physics. It's all over the place. And it started back in the day with the Greeks, where they were trying to pin down the nature of reality. And they couldn't ever get to what a priori things are, right? So what they ended up doing is saying, hey, or later, right, they came up with their points, their concepts aligned by looking at the real world and coming up with some axioms from observation. That is a useful thing to do. I say still do that, right? That'll show up. However, later, when the concepts of proofs and proof systems came out, things like set theory, what later developments ended up doing was creating the concepts of indeterminates, right? That means that we come up with a set of symbols and we leave them unspecified, right? They're called indeterminates. Like point is an indeterminate, a line's an indeterminate. We're not even going to say what they are. And instead we're going to focus on the relationships that they satisfy. That's kind of hinting that whether or not the universe just is full of this sort of, unspecified potentiality. You can call it all, God, whatever. It's just everything that can and be and everything can be type stuff. Maybe it's that way, and then we interact by picking out or conceptualizing something that then has a form that allows us to create math, right? Specified things. Or whether it's that reality is very fixed, but our ability to access it is limited, right? Like, for example, we pop into this world, and then all of a sudden, a little later, we're like, huh? What? How? Why? How are we suddenly here? How's things existing? Whether that's the case or not, the idea of sort of an indeterminacy, which, along with things that we can specify or determine, like those two together kind of are reality, is what I'm proposing, right? And the reason why we get stuck is because the nature of reality is such that, yes, they expand. If you don't specify them, they expand to all possibility, right? Things just are at all of reality in a way. And once you decide to filter that, right, by coming up with some concepts, right, and then you write them down and you create axioms or rules or whatever, and then you start following the logical consequence, what you get is something that is sort of picked out from what could have been, right? And so that's the idea. Now, in here, there are some things that just keep showing up that when you try to write stuff down, you're assuming something, and it just shows up all over the place. And what that is, first of all, when you take a piece of paper, right, to write something down, there's something already kind of hidden on that paper that already does exist a priori. And I would say it's one thing that needs not be specified as an indeterminate, and that is the blank, right? It comes as a blank piece of paper. Nothing, the concept of nothing, of emptiness, is everywhere. It's already there. So you have something to work with right from the start. And so I'm going to say, hey, if it's something that turns out it was there without needing to have an assumption, then I'm going to take that and put it at the top of my hierarchy, my conceptual hierarchy. The other thing that comes up, right, is that we have the concept of same and other, right? Is A the same as itself, or is it there's the concept of one, right, one thing, and then there's the concept of two things, two different things, right? And that's the same, the concept of things in relation to themselves and things, two different things, A and B, related to each other. And so because that comes up so often, right, and if you try to go further without specifying this distinction, same, other, you get into concepts like trying to create ordered sets, like ordered tuples and stuff. But before even that, you have a natural concept of just same and other. And I choose a circle to represent sameness because when you do like maps from functions to itself, you can have self loops, things like that, and that seems a natural thing to use. Also in group theory, you can code it on a circle. That's when you're talking about automorphisms from an object to itself. That shows up in physics. So a lot of reasons I chose a circle to represent the concept of sameness, right? Including how we interact with thinking about same things, right? Self-interaction. And then other, I chose just an undirected edge because you can put something on one side and something on the other, and those two could be different things. So the concept of distinction and indistinction are coded at the next level. So nothing first, then the concept of same versus different. And then we go ahead and create a directedness, and that allows us to create things like tuples, like A comma B, like what you see down here in this Cartesian product. And that's sort of like saying, okay, in the first one, right, using a principle that, hey, everything kind of, first of all, everything was all potentiality, all things that could be everything, right? And then we chose a circle and a line, and I chose it to be undirected, so the direction is indeterminate, right? It means it's everything that can be. If there were 50 possible directions, it would be all 50 with equal probability, right? It would be, if there's 50 ways to relate directions between one thing and another, then another structure, then there would be, it would take up all of them, right? And then you could throw in probability there because that matches quantum mechanics math, right? And so by operating at this level, it's like once we've go ahead and created a structure to kind of pull something out like a circle and a line, and this concept of same and distinction, if we make no additional assumptions, we're as close to, it's going to take up as much of reality as it can, right? That's the expansion principle, or whatever you call it. I'm calling it principle number one, which I'm trying to be super concrete with it in this instance, but basically you want to describe things as close to the idea that it inhabits or expands to occupy as much of the rest of reality as you can. It turns out if you do that, it makes counting things super easy, right? Or a lot easier conceptually, right? There's a hidden concept of independence in here, but I don't know whether independence, like when you can separate things into a product of two things that are independent, whether that's even necessary or whether it's the same or different than the concept of being able to look at a system, subsystem, and consider all the rest of it to be inhabiting as much of reality as possible. Because I didn't specify independence necessarily, but it might be that those two, those are related. It might be that they're equivalent. It might, but if that's the case, then if you can separate all reality from a particular piece, it means you can factor it as a product of something, of two somethings, right? What you're looking at and the rest. And that does happen in like wave functions and things like that. So that might be something to look at later. But for now, when I was doing the counting, that came up. Okay, so with that in place, right, I'm going to take an example. And the thing that is, like, if you look at just the number of functions from a set A to a set B, that is really, really constrained, right? Because the way a function is defined as, in fact, a relation between A and B is defined as just a subset of the Cartesian product. Now, Relations mean you can have as many edges between an element of A and however many elements of B, the set B, there are, right? And that is the least assumptions, right? So you would think that, and if you look up here, it would be like how close to every, like just potentiality, right, can you get, right? And if you're going to describe some concept of A and B relating to each other, the way to do that the most naturally is to let the thing take up as many possibilities as you can. And in that sense, well, with the assumption, you have the directed edge right here. So we're describing things in terms of this biggest piece, and we're using the set A here and the set B, which is higher up on the hierarchy. Then we have the Cartesian product, and then we have next to it another way of describing relations, which is edges, undirected edges. Again, we're using this one. And when you look at this, right, you can have edges from A to E, A to F, A to G, right? There's three of them. Or you could just have edges from A to E or A to F. You can just have a directed, or just an undirected edge from A to E and nowhere else. And for all those possibilities, you can count up how many of them there are, right? And it turns out there are exactly, if you go down here, you can create a binary number, E, F, G, where you're just looking at A, and you can put a 0 in the E spot if there's no edge from A to E at all. Like it's just empty, right? Here's an example. If you look at C, right? C to F, right? There's nothing, right? In fact, there's no edges from E, C to anything else. So what you would have if you were doing this, if you were using C, for example, instead of A, you would just have 0, 0, 0 because there are no edges from C to any of them. You could, if you're looking at D, right, there's exactly one edge from D to G, so you would put a 1 in G spot and you'd put a 0, 0 here. And so if you're looking at any one of these, right, if you want to count up how many, it's just the number of binary digits you can create that has a length of 3, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There's a total of 8 of those. But that 8 happens to be equal to 2 raised to the power of 3. Now, power of 3, where did 3 come from? 3 is the cardinality of the set B. So the number of relations between one element of A, a fixed element of A, and the set containing 3 objects, A, E, F, and G, is equal to 2 raised to the power of the cardinality of that second set, which is power of B, right? Now, while counting the elements of A, right, the rest of reality, which is whatever's happening between B, C, D, and D and all of these elements of B, are allowed to do all the things that they could. That's the expansion principle. Well, they're all kind of identical, right? We have them lined up, and for each of these B, C, and D, they're exactly, right, if you want to count them up, there's exactly, well, how many subsets are we able to pick out? Well, in this case from A to E, right, all the A to E stuff is right up here. So the 3 bits, right, were for this down here, we're actually just sort of taking this first row and creating a binary digit of length of that first row. How many elements are in that first row? And if you look, if we do that for each one of these can do whatever it wants regardless of what A does, what C does, and so forth. That's sort of like independence, right? So for each of these 2 to the power of A of B things, right, there's actually, well, how many different it's actually picking subsets of the Cartesian products. And how many of the subsets are there in this piece right here? Well, in the whole thing, it's just the cardinality, it's the number of subsets of however many sets in this big block, which is 3 times 4, right, which is the cardinality of A times B, minus the cardinality of B, right, or the minus the cardinality of B. So, in short, right, if you take 2 to the power of B multiplied by 2 to the power of the product of A times B minus the cardinality of B, when you put those together, you just get 2 to the A times B. Cardinality of A times cardinality of B. Another way of seeing that is that, hey, all the relations you can create here is just picking out a subset of the Cartesian product. But that is how many, equivalent to the number of functions from the Cartesian product to the set 2, where you can have 2 as like true and false, where you look at the things mapped to true, and that picks out just the subsets of that are included, right? And it turns out the number of functions from from A to B is equal to the number of subsets that you can pick out from here, which is equal to 2 to the capital, or the cardinality of A times the cardinality of B. So that's another way to look at it. And so all of that just goes to show, okay, now there's something interesting, right? We made as few assumptions as possible, including choosing the directedness. And from this equation, and even from these undirected edges, you could realize that, hey, there's really no specified order here. So the number of edges or relations from A to B is the same as the number of relations from B to A, because there's really no direction to it. That is natural if you don't use arrows. But if you were to use directed arrows, that would become less clear. It would still be clear in the math, but it would not match with the picture. And so what I'm saying is and I did it with the arrows first in my head, that I realized, oh, there was actually an inconsistency that came up later that sort of suggested, hey, sure enough, I should move up in this diagram and describe things as high up in this hierarchy as I can. Well, in this case, I needed or wanted some kind of edge to make distinctions, right? Because I was going to make distinctions. And there's even a concept of nothingness that's going to come up in a minute, right? Now, that's at the top, right? And so, because nothing is at the top. Actually, nothing is everywhere. This page is full of blanks, right? Blanks mean not blank spaces, but actually nothing, right? You didn't put anything on the paper. It's everywhere in space. It's the concept of, you take this cell phone, and having nothing in addition to it is just the cell phone, right? You can have no space, no symbol, no object, no mass, no space-time, no nothing. That is the concept of nothing, and it's always ever present. It's there for free. And that's why I put it, whenever specifying things, I put it at the top of the hierarchy. So if you can describe things in terms of some concept of nothing and operations you can do on it and concepts of distinction, you're going to get some clean results when it comes to counting things. And so, and I'm thinking in terms of counting stuff right now. I found that to be really useful for this concept, to bore this out. So, long story short, if you start then thinking about functions, right? Functions create an additional restriction, right? It says that there has to be exactly one, not just edge, but directed edge, right? You would have to use this concept. So you're going further down the thing, and you're adding more restrictions than what a relation would have. So you might expect that, hey, the system wants to get as close to undetermined as possible. We're forcing it to we put some restrictions on it. Now we're putting more restrictions on it. We might see that sort of show up in the math, maybe even as an indeterminate in the math, right? And sure enough, if we look at the number of functions, first, a function is, there's exactly one, for each of these letters on the left, right, these elements of the set, there's exactly one arrow from that to that element to one of the others, right? So if you do it as ordered pairs, you have to pick one of these three in the first row. You can't have all of them. And if you did do that, then going back to the binary representation, right? If you put a 1 in the first place to indicate that there's a f of a equals e, right? Then all the other ones, then f of a cannot equal f or g if it's a function, right? So that means that there would be zeros in the other two. So you could put a 1 and then 0 for the f and 0 for the g. Or if you want to map a to f, the middle one instead, well, you'd put a 1 in the middle space and then zeros in e and g. And then if you wanted to map a to g, right, you would put a 1 in the g spot and zeros in e and f, right? So really what it looks like is just a 1 moving across here. 1 in the E, then it's 1 in the F, 1 in the G, and zeros everywhere else. So if you ask how many ways are there to do that on one element, well, it's just the cardinality of B, right? the right one. So the cardinality of B, right? There's three different ways. There's three set elements in the set B, and the rest of it's going to do all that it wants to do, right? So if you look at that, right, each one of these is an identically independent sort of system, right, if you want to call it that. For each one of those capital B things happening here, right, for each one, there's another set of capital things B things happening here. In each one of the instances where you could pick one of these, there's also all three possibilities here. So really, when you're looking at B, it would just be capital B for the possibilities here times capital B again for the first possibilities here for the A row. And then if you look at C row, well, B and A can do whatever it wants. So there would be capital B possibilities for the C row multiplied by the capital B possibilities for B row multiplied by capital B, cardinality of B possibilities for the A row, right? And if you go to D, it's the same thing. So it's it's cardinality of B times itself 4 times, one for each of the rows. But how many rows are there? It's cardinality of A. So if you multiply cardinality of B times itself A times, right? Then that's just cardinality of B raised to the cardinality of A. So it's B to the A power, right? And that is actually correct. The number of functions from A to B is equal to the cardinality of cardinality of B raised to the power of cardinality A. And when you write that, right, what happens if if A and B are the empty set? Well, then you get 0 to the 0. And 0 to the 0 is an indeterminate form, right? It's hinting, I question, right? First of all, we created the restrictions and then further away from indeterminacy, right? Indeterminate means it could be anything. There's more than one thing it could be. I'm saying it could be everything, anything. Then in the math showed up an indeterminate form. So here's a question. Like, if you look at systems that have an indeterminate form, is there a way to go up in this hierarchy or something similar where if you were to go further up, that indeterminate form would go away and the whole thing is consistent, like it has an equation that sort of makes sense? Well, if you look up here in terms of relations, again, relations use the concept of, it uses the concept of nothing and something, right? Or it uses the concept of other and the sets A. These are all examples of somethings, right? Nothing is actually is more close to the thing, to primary. Somethings are things we have to write down, and I'll get to how I'm choosing to express that here in a minute. Basically, if you put a symbol on, if you write ink on a paper, that's the something, right? I'm choosing to put something on the paper, it's a something, right? That doesn't mean that's what something conceptually actually is. It's just what I can access and make it really concrete. So I'm taking all potentiality and picking out one that I can actually do something with. So I've chosen that if I put a symbol on this page, it represents something. The blank represents nothing. Some things are things that I write down, but nothing was something that was already there, a priori. And that's how I'm organizing it in my mind for this exercise, right? I reserve the right to change all that and to go in other directions because I think the flexibility helps to start seeing things differently and then coming back to what feels, and since in experiencing the concept internally, what seems to line up and make more sense to me in the bigger picture of this idea of this reality and nature of reality. And so, long story short, if we look at the relations instead, it's further up on the hierarchy. And if we put 0 in this equation, well, it's just 2 to the 0 times 0, which is equal to 2 to the 0, which is just 1. That's a well-defined function, right? It's a math. It's not an indeterminate form. And so if you look at the number of relations between the empty set and itself, there's exactly one of them, right? And so by moving further up, right, you get something that gives rise to an equation in the algebra here that remains consistent across all possibilities of the sets that you're working with. Granted, I'm using empty set and regular set theory. In this case, I'm sticking with finite sets because I'm wanting to do counting and stuff, and I don't want to make it. I want to get as much out with as simple of a thing as I can to try to bore this concept out, and that's what I'm doing here. So the question is, that's actually pretty much all of it, most of it. The one thing I can say is when I experienced this, wrestling with the concept of everything, right, all potentiality, really, and feeling it, right, really made doing this calculation, this 2 to the a times b, in my head, and the way I was feeling the thing, it allowed me to derive all this sort of in my head, right? And then when I worked it out on the paper, it worked. That happened when I woke up this morning. I was feeling it, and again, there's some things I do with meditation that where I can sort of feel into things, almost like I'm moving through this space of reality and I'm getting feedback from it. If I try to go down this way, I feel something that says, hey, you're off a little, come back. And then shortly thereafter, that feeling emerges why, right? And at first, I just woke up and started thinking about these ideas, right? And then I was like, well, how does this relate to like the bigger picture of this nothing something, or the fundamental nature of reality, where just everything is possible? And then more feelings came in, and shortly thereafter, this all went from the real narrow piece to the whole big picture, where I could see how and feel and experience how all this was related. And then thought about it throughout the day, and even how I was going to represent this. I worked that out in the meditation, and I came back and wrote this down. There's actually 2 pages, but I thought I would just explain it in this one. What was on the 2 pages was just, the second page was everything I just said about, just described to you with pictures, and just pointing here. And that's what I got, And when I think about this, I also feel just super centered, super here. It's almost like I'm aligning myself with the nature of reality, and by that I just have this super calm, present feeling. So, and that goes back to like mysticism, and when you're closer to nature and you're aligning yourself with how things actually are, you tend to be more balanced. And so this is also an exercise to center myself, so it's a spiritual practice as well, essentially, or mystical practice as well. In the sense, you can say mystical, you can say meditative, you can say for personal health. What I'm experiencing is that because this seems to align, it feels like it closes a bunch of loops, and it just, or even if the loops are open, it just feels super centering, right? And that's just thinking. So that's where I'm at. If you have any questions or concerns, well, I may or may not share this, but it's my journal for the day.